Started here. This is a topic which maybe we're returning to for an additional lecture or two as time allows later. Today, though, I wanted to introduce some of the basics of this topic and talk what I consider the most important sort of features of it for your projects up front. So last time we had talked about, we had given a first sort of look at the issue of creating test cases. And when I say the word test cases, I've learned over the years that students often very reasonably don't know what I mean by a test case. What I'm talking about is a very, very specific plan for testing to the level of, exactly what input you're going to be giving. Exactly what things are going to fill in those edit boxes, those pull down to the drop downs, click on those radio buttons or check boxes or whatever. You've planned that out. You know what steps you're going through with the system in a fashion to test out its features. Or it could be so that'll be at the black box level through the UI, or it could be, you call this function with these particular values for the parameters and this particular data structure, etc., and you see what it returns. You're checking how does the system behave with particulars and confirming that what it does or what it returns, what it modifies, the state it leaves the global data structure in is appropriate. Okay, it's a very, very specific case of testing. And, a given system, if you have a bug party, or if you are doing unit tests on your code, you might have many test cases. And those test cases are designed to build confidence that the system is working correctly, both in the sense of doing the right things when the inputs are correct and doing the right things when the inputs aren't correct. Right, whether it's user input or input to functions. Now, we may come back to that issue of doing the right thing when things aren't correct. Often for methods or functions, we have preconditions, and the preconditions promise behavior if those preconditions are met. They promise certain behavior, but all bets are off if they're not met, and so you might not be as much testing, what happens if it falls outside the preconditions. But certainly for user input, that's an extremely important thing, because calls to functions, it's we as developers who are making them. If those functions are for use only within our code, presumably we can make sure we're using them correctly, and we put in assertions to check that. If we're dealing with user input, that's not under our control, and we have to be prepared. A user might use the system in a way that's different from what we wanted or intended. Okay. Anyway, brief comments. So I'm going to talk about coverage testing. This was some comments that I actually had from last year, and I realized most of these are still needed a bit. I thought most of the project teams had structures that were actually fairly easily navigable this year and decent readmes. There's a little bit of additional need there. Going forward, I would like access to the system as created at the time of the report, at the time of the hand-in. So if you've got an app with Ionic running on Android and iPhone, I want to be able to install it on phones and see it. I was just talking earlier with Janelle about for the Oculus Rift hardware, this is probably going to mean coordinating with the teams to getting some time so that we can be with the hardware and test it out. We're going to be wanting, going forward, to start testing for these incremental deliverables, the code base, at the time of the deliverable. And if you're dealing with a web system, I'll need access, and the TAs will need access to the web system. Okay. We will be looking for testing at different levels, unit and integration testing, some evidence of manual and automatic testing, and beyond this, because its purpose is rather different, is the smoke test. And I had mentioned earlier to Chris that the job of the smoke test is to make sure it's worth your while doing a pull from the latest updates pushed by someone, that they haven't so broken the system that it'll be bad for you to get their changes. And so it should be testing things that are key functionality of the system without which it's not worth getting. That the system allows a login, that the system can draw data from the requisite database, that it's able to connect to the server to get the requisite information, to download recent incidents. Make sure that basically the system's not horribly broken. That's the job of the smoke test. It's not so much to find new classes of bugs as to make sure it's it's worth getting this latest refresh of the code base, that it's not so hosed that people should hold off. And I know some of you are using different frameworks for testing. It varies a lot from team to team, but when it comes to coverage testing, whether it's with Istanbul or JS Cover or Blanket.js or I think it's Emma, you should be able to have some sort of coverage testing. We'll talk about that. I'd expect to see some sort of test harnesses, code which calls off to pieces of your functionality. They're the same pieces that are being invoked through the UI, but it calls them manually, perhaps, to just make sure they work together as anticipated. So some sort of test harnesses. And mocking is very good to see, and some sort of code coverage metrics over time. I think there was one of the teams. What was the team that had code coverage already? Yeah, that's great stuff. Great stuff. Should really, at this point, I should create an extra category in the marking rubric for that, because that's unexpected. So, but going forward, we'll want to see this with more and more. Okay, so speak about coverage. I'd like to talk about coverage, different types of coverage, state-based, transition, and outside of this lecture, probably after the break, we'll talk about prime path coverage and maybe about constraint-based coverage. So the idea with coverage testing is coming up with systematic test cases for a system that will exercise functionality of the system. We talked last time about picking corner cases, boundary cases, picking a case from each equivalence class, and that's good. But sometimes we have a structure of the system in mind. We have some sort of set of pieces of the system that we want to cover. Maybe they're the states of the system. Maybe they're the streams of the system, or maybe they're the transitions in terms of possible conditional paths the code could go through. Or maybe it's transitions between pages of a web app. And we want to cover all those transitions to make sure we've exercised the functionality of the system. And so today we're going to be talking about that. And what we talked about last time is relevant because we're going to be, that too is an attempt to kind of exercise different cases. But here the focus is on graph-based methods. So here's a state or activity diagram for a common thing that you folks probably have a fair bit of experience with, which is automated teller machines. These are these machines that give out banknotes or bills if you have a debit card, right? There's an ATM card, and the key point is here: the ATM, the automated teller machine, it has some functionality, and we could talk about the functionality, we could write it down in requirements, we could talk about use cases, but fundamentally we should be able to, for most systems, characterize the function of the system using a combination of nodes and edges between nodes, where often the nodes represent a state the system's in. So maybe it's prompting for a pin while that pin is being entered, a state of checking the pin, or confiscating the card if the pin was incorrect, ejecting a card. These might be states that the system's in, and there's transitions between them that are conditional. Right? So if someone inserts a card and the card's not recognized, it ejects it. If they insert a card, it is recognized, so we'll wait for a pin. You enter the pin. If the card is expired, it may be confiscated. It sucks it in and doesn't return it. It says your card is expired. Please contact us for a new card, and it keeps it. Alternatively, if the card is not expired, it may check the pin. If it's an invalid pin, it will keep on asking for the pin up to 3 tries. But if it reaches the 3rd try that it's incorrect, it may confiscate it, thinking that you're trying to break into this card. Seen that happen once, about 20 years ago. It sucks it in and confiscates it. Here, if the pin is valid, then it goes to prompt for the transaction. You select an account number. There's lots of detail that this hides. It's an abstraction, and abstractions hide detail. It hides a lot of detail about the situation, but it captures some basic sort of structure of the system, right? In terms of its flow, the flow of logical operations. And I think every system in this room could be diagrammed out to one degree or another in a diagram like this. What's going to be different about the systems is the details that are hidden will be very different. For example, I would imagine for the virtual surgery, the VR surgery with the Oculus Rift, there's going to be a whole state where the user is going to be interacting with the system in a continuous way, moving around, looking at things or what have you. That's just going to be maybe one state of interaction. But then there's going to be other states of getting the system maybe configured, interacting with buttons, so the system goes into different modes, a Windows mode versus a VR mode, etc. For those who are working on the long-term care app, there's going to be certain modes associated with screens of the app, maybe where you're taking a photo of an incident, or you're entering some information, or you're checking on a previously reported incident and you want to see what the current status of that is or what have you. There might be particular states associated, maybe with pages of what's on the screen. For a web app associated with browsing, online resources for real estate, there might be pages that you can go to or what have you. Or if there were an app version of it, might also be screens. So different systems will map to this in different ways. The states will have different meaning. A page, a web page versus a screen. Or a functional state of the system. It's waiting for user input about this. But the point is that most systems we can diagram in this way. Most systems we can diagram at some level. Is there lots of things this won't capture? You bet. But there's lots of things it will capture about the structure. Okay? Even if it's just a login screen, you have a certain number of tries, etc. So you should be able to create a diagram like this for your system. And in fact, one of the groups had a very nice diagram for their system already. It was well colored. It had different types of edges and nodes, and etc. So we're going to talk about using a diagram like this to plan systematic testing. Systematic testing through the system. Okay. So this is one diagram. Here's another one. This is a bit dated now. Airline tickets. This was reflective of a state where you'd actually get a printed ticket. But the overall idea, much of it carries over. So, you here have some reservation you like to have. You actually make a reservation, and that reserves a flight for you. By paying the money, now you're in a different state. You're in a state where you've paid for the reservation. You have a reservation that's in fact confirmed. And then there used to be a state of being ticketed. And then, by using that ticket in the actual occurrence, you'd use it and it would go to a different state. The point here is there's several stages you could be at, and this is still true, where I can make a reservation and it's good for a certain number of hours until I pay. And after that, if I don't pay, it's freed up for someone else to use that seat. And you might break down other seats. Do I have seats assigned yet or not, right, on the plane? Here, there are transitions. So if you don't pay within a certain time, it may be canceled. If you do pay, you can still cancel it, although perhaps with some cancellation fee. You might do that even after ticketing in earlier stages. So this would be an example of achieving state coverage, what you see here. Why do I say this is state coverage? Anyone want to hazard a guess? Why is this state coverage, what I'm showing? So I'm saying these circles are states. Why do I call it state coverage?
Because you're trying to plan a path that can hit all of the states.
Yeah, and it's not just one path, actually. It's a collection of paths that collectively, together, they hit all of the states. Now, notice what this is not. I'm not trying to perform a Eulerian walk on this system or a traveling salesman type situation where I can't go through a given state more than once. Each transition or each state, I can actually visit more than once. No problem with that. The MAID state, all of these different use cases go through MAID, right? I'll visit MAID. That's fine, but it takes them all three of them to collectively mean I have visited each state. Now, you may ask, well, why these three paths? The three paths are not particularly privileged here. There may be other paths that will visit each state. In fact, there are. Maybe instead of going down this cancellation from MAID, I in fact want to explore where I've paid and then I cancel that. And either one, I've got to cancel by customer. But the point is that if I don't visit each state at least once, it's hard for me to pass the red face test. It's hard for me to develop a conviction that the system is working properly. How do I know that cancellation by customer state is working properly in its functionality unless I've at least visited it once, right? So there's a certain plausibility that if I haven't reached a state, the claims that my system is working are fairly hollow, because I don't really know that for sure. I've never really gotten to that state to try it. This is the most basic form of testing, and we'll talk about it, but it's one that's useful to reason about. We'll talk about another level of testing, one in fact in a hierarchy, much like the language hierarchy that you folks perhaps are learning about in what is it, 362 or something, with language hierarchies, regular expressions and context-free grammars and Turing machines, yeah? Huh? Is that 360? Yeah. Is that covered in 360? Okay. I thought there's also machines and 364. Okay. That sort of machines, that covers more of the sort of computability hierarchy, I think, about what can be done by each level, pushed on automata. Beautiful stuff. Beautiful stuff. But not the focus of today's lecture. But there's a similar hierarchy here, because we're going to have different levels of coverage. And it turns out transition coverage is going to give us everything we get through state coverage, but more. What's different here? And this is not a trick question. What's different here? We're covering, yeah.
We're covering the transitions instead of protecting each state.
Good call. Remind me of your name, young man.
Brandon.
Thank you very much. Names go in one ear and they come up the other. So I appreciate that. So here we're covering every single transition, not just every state. So the last one, for example, we reached this point of cancellation only with one of the three transitions here. And we have some confidence that the state is working since we got there once. But whether it works for each of these transitions, we didn't have a lot of evidence to go by that it's going to work properly for each. Here, and the processes involved in cancellation may be rather different if it's ticketed. There's actually a physical ticket that's been given. What you need to do to indicate that it's canceled may be somewhat different. You don't want them to walk in and use it, redeem it, and only to find that it's no longer legit. And so in this previous case, state coverage, we didn't cover those two transitions. And again, it's hard to have confidence we really tested it well, but this is a whole nother level of testing. Okay, and we can do, create similar diagrams for many systems. This is actually a process flow system involving repairs that we'll be talking about. So how you go about requesting repairs. Maybe it's for a laptop, or maybe it's for a smartphone, or what have you. Here, we can map out kind of the states that we're in. No maintenance is required. It's waiting for pickup. It's under repair in a maintenance station. Maybe it has to be sent to regional headquarters because it needs a new motherboard, or maybe we're waiting for a particular component. A replacement for the card reader for the SD card or what have you. Maybe it's in main headquarters. Maybe it's in a repaired state and it's about to be returned. So we can map out a process, and again, we could try to satisfy transition coverage with different transitions through that. That's for a process. Alternatively, we can perform the same sort of diagramming at the low level. Is anyone in here in the compiler course? No? No? Okay. I would recommend it to folks seeking to understand principles of software engineering. While it's a slight diversion, I would just note that compilers, perhaps more so than any other system I know, bring together under a single roof many aspects of software engineering, and in fact principles of computer science, including language hierarchies, etc. And there's a famous text, probably the most famous text in the compiler sphere. It's called the Dragon Book. Do you folks know about the Dragon Book? No? Okay. Dragon Book is by Aho, Sethi, and Ullman. In earlier times, I think there's now an additional author on it. But anyway, it has a dragon on the cover. And the dragon's supposed to symbolize the complexity of compiler development. And it shows someone trying to slay the dragon, trying to take on this complexity and manage it. And it's a big software engineering exercise. You'll learn a lot of software engineering principles from a compiler course. But more than that, you'll also learn that some principles that apply at the high level also apply at the low level. For example, here, if we think about low-level code, we think about lines of Java code, or Scala code, or C code, or C++, or Swift code, or Objective-C, or whatever. Pick your language. We can actually diagram out the flow of this code using nodes and transitions, just like we did those higher level things between pages or web pages or functional states or what have you. So an if statement over here might unpack into so-called basic blocks, each of which is sequential in its computation, that have several features. So for example, N0 is the basic block that proceeds testing this predicate, is x less than y. If so, it goes to this basic block N1, which are the couple statements within this if consequent, and then falls through to N2. By contrast, if x is greater than or equal to y, this test in the if is false, and so we fall through to N2 directly. Similarly, if we have a while loop, we could diagram it in this sort of way, and you'll see that there's this back arrow reflecting, well, what does this back arrow represent? Yes?
Is this an abstract syntax tree, or what's the connection?
No, it's a great question. In compilers, we actually have different representations of a program. And it turns out that an abstract syntax tree is a way of characterizing the structure of the source code, typically. It can be applied at intermediate code, but it's generally the sort of, so when we write a statement in Scala, or we write a statement in Java, or C++, or C, or what have you, we can actually diagram out the statement, sort of like I don't know, like in high school or junior high, did you folks deal with like diagramming sentences? Noun phrase, verb phrase, preposition. Okay, prepositional phrase, clause. Not Santa Claus, but you know the clause is a part of speech. It's kind of like that. You're diagramming the components. So there's an expression. Expression can consist of an operator, and it could be a simple variable name, or it could be one expression, an operator, another expression, and that's a representation of a program. But another representation of the code has to do with the flow of control of the code, how it runs from one thing to the next to the next. And there we're concerned about how one statement leads to the next, And this is a type of diagram that's called the control flow graph, CFG. And it sort of is another way of describing a program that focuses on something else. And those two, in a given compiler run, when you compile your Java program with Java C, both those things are being created and representing the program at the same time. And in fact, the abstract syntax tree ends up contributing to the creation of this guy. And that's all part of slaying the dragon, so to speak. Okay? Okay, so ladies and gentlemen, here we have a while loop. This back arrow represents looping back to the top, right? As long as x is less than y, we perform these operations, we loop back. Once again, we can diagram the program out at this level, this low level, using in fact blocks, okay? And I'll even show. Here's an example of C code being mapped out into these blocks. These basic blocks, just like I've shown for that if statement and the while statement. So we take a bunch of C code that just looks like this, and we turn it into a graph. And by turning it into a graph, what can we do with it? Why do we turn it into a graph? Yes?
State coverage and transition coverage?
Yeah, we can reason about state coverage and transition coverage. And in fact, ladies and gentlemen, whether it's running blanket.js or Istanbul or Emma or what have you, Cobertura, when it's reason about coverage, it's actually talking about the standard for most of those is state coverage. So it's asking about what fraction of these states do you actually get. And you can do that at this low level, where we're dealing with pointers and if statements and whiles, or we can do it at this high level, this sort of functional level. And for your assignment, for your projects, what I would like to see, for those who don't have it already, is I would like to see diagrams of your system created in this way. Now, it's a bit late for that for ID2, although my heart will leap if I see it for ID2. If I don't see it for ID3, my heart is sick. Okay? So creating a map of your system like this shouldn't be too hard at a high level. Yes, it'll leave out a lot. That's fine. It's part of the deal. It's an abstraction. It hides details. But you should be able to use it to reason about state coverage and transition coverage. Okay, so let's unpack these a little bit more. The key steps in coverage procedure. We're going to be talking about state coverage, transition coverage, prime path coverage, probably logical coverage. The idea is basically the same, and this is a very testable thing. Very testable. Or shall I be more specific? It's very examinable. So basically, 3 stages here. We identify the set of things we want to cover. Let's say we want to cover states. Or maybe it's transitions. Or maybe it is prime paths. Or maybe it is pairs of transitions. Whatever it is, we identify the set of things. We say this one, this one, this one, this one. We identify the set of them. Next, we develop a set of abstract scenarios, paths, of flow through the system that include all the things we need to cover. So we imagine paths through the system that cover all the states, for example. So we think, okay, so a user comes to this system and they do this and they do this. This is abstract. We're not dealing with test cases yet. We're not dealing with specifics. We're saying, okay, they make it and then they cancel it due to non-pay. Or they make it and they pay for it and they ticket it and it's actually used. Or they make it and then they cancel it. And those are abstract paths. They cover the different states. And they travel on transitions because the only way you can get from state A to state B is if you take a transition directly or indirectly through other states, right? Okay, so we figure paths through the system from start to finish. You don't magically appear in the middle of the system. From start to finish, paths through the system that will cover the things you want to cover. Maybe the things you want to cover are the states. So you do paths through the system that cover the states. Maybe the things you want to cover are the transitions. So you come up with abstract paths that cover each of the transitions. But at this point, these paths are abstract. And what I mean is they're not specific test cases yet. They don't involve specific inputs that will realize that path. They're just paths through the system. And then, ladies and gentlemen, we need to figure out and address the next level of need, which is more specific. We want to come up with concrete test cases, specific sequences of inputs that will realize these paths, make them happen, that will force us to go this way or that way. So here the user is entering a particular thing, or our automated test, the tester is entering a particular thing manually, or the automated test framework is entering things. Okay. Now these test cases might exercise additional paths not included in the specific paths, and that's okay. I mean, they can loop around, but as long as we're hitting these paths that we want to cover, we're okay. Okay. And these are concrete. These are specific things you can type in and click and do that will actually realize these things you want to cover, that will in turn cover all the things you want to. So this is going from high level, what do we want to cover, to very low level. Like, what do I need to type at this stage for this test case? All right? So let's unpack this a little bit. Okay. Okay. So when I say I want to test this code, so here's some C code. Okay. I'll come back to a few general points there, but here's some C code. This code actually is a CGI code thing. So here we are giving in, as we are wont in C, we are giving in 2 character pointers. So one points to an encoded string where a percent sign, 20 is used to encode a what? Yeah, space in a URL, right? Or we'll have the and sign encoded using a percent, thing, etc. Right? We'll have question marks in there, etc. And we want to turn it into a string, a corresponding string that's decoded, where the spaces are turned into spaces. So we give it a pointer to a buffer where we're going to write the code into. Now you have to be careful about the length of this buffer and so on. I'm going to abstract away from it. This is from this great book by Pezzi and Young on software testing. I'm using it from that example, and it's a good one. So here we have this routine. It takes in an encoded string, and it's going to basically derive and functionally return a decoded string. So it's going to put into that place a decoded string, the version of that input string that in a decoded form. Make sense? Okay. Now in order to do this, it has as you might expect, a while loop. Goes through, loops through it, and looks for, what would you be looking for? What would you be looking for? If I sat you down and said, this is not a test, this is an exam, this is your final exam, right now, today. Close the door, I know, you'd report me, but with good reason. But if I sat you down and I said, okay, I want you to write this, or if I were interviewing you as a company, and I said, okay, I'm running this small startup and we need really good whiz-bang programmers, I want you to write this, what would you be looking for in that while loop? What would you be looking for in that loop? What would you be doing?
Characters that need to be encoded.
Yeah, you'd be looking for these special characters. So you'd be looking for pluses or percent signs, these special characters that need to be unpacked. Okay? They need to be turned. So if you have a %20, somehow we have to look for the percent and look for the numbers after that and reason, okay, the 2 and 0 are in hexadecimal, and we need to turn it into an appropriate ASCII character, 32, which is 20 in hex, and it's a space. Okay, so we're going to insert a space. So this is what this is doing. This is a while loop, and this is an illustration of that. But this is great. This is just the nodes and edges, right? The nodes and transitions, the vertices and transitions, however you want to call it. In order to test it, in order to achieve certain paths through the program, I'm going to come up with test cases that exercises. A test case set that collectively will cover this. And here, this is one test case set. I enter a URL that's just a space. I enter another one that's test, another one that's test plus case %side 1D. So that's a hex thing, and then adequacy. This is another test case set that will cover all paths through this. And you'll notice that these are very specific things. They are things that I call it with particular characters, particular strings that I'm calling it with. And any given one of these, I would argue, T0, T1, T2, T3, or T4, is enough to achieve state coverage of this. Any one of these, if I give it these ones, I will reach all the states here. Those are test cases. I'm running with a specific input. And this is, in fact, a collection of test cases that will achieve state coverage. Okay? Notice these test coverages are not some ethereal thing. They are very specific words that I could type in when testing this. I could have a test harness that runs it with these test cases. These are specific inputs. Does that make sense? And I would argue that these will, in fact, reach all the states of the system. Okay, so let's talk about this a little bit more. That's where we're going. Okay, so for a given situation, coverage techniques let you derive legal paths through the program. These have to be from the start to the finish. You don't magically appear in the middle of the program. You have to get there. You have to start the program up, enter this method at its entry point, right? Or start with the ATM back here. Start with the ATM at this point, and you're trying to reach these other points through having started there. And you got to end up somewhere at a place that you leave the system. Maybe it's card ejection. Maybe it's leaving through successful transaction or what have you. Okay, so here we're finding these paths from start to finish. So we'll exercise the level of coverage, hitting all states, hitting all transitions, whatever it is that we want to achieve. And then we're going to find these small set of specific test cases that jointly will cover all these things. And these use particular inputs. So that's exactly what I just showed you. That's what this was. Each of these is a specific set of inputs that collectively will cover all the nodes. Comfortable with that idea? So we are always testing in the particulars. We're testing specific inputs. So why would you graph these things out? Because you can reason about them more easily, you can document them, but we can derive these test cases. And in some cases, researchers have worked on automatically deriving test cases that will test this code. So you give it some Java code, and it will spit out certain inputs that will reach all places within the code, or all transitions within the code. Okay. So this is the idea here. Now, there's some challenges with this. One challenge is building up this graph from a description, and I give an example here. This is from Pezzi and Young as well. So here we have a description in English, and we go and we unpack this we turn it into this sort of diagram. It's not rocket science. Let's take an example here. If the maintenance contract number provided by the customer is not valid, the item follows the procedure for items not covered by warranty, right? So here at the repair station, if it's an invalid contract number, it goes to the maintenance without warranty state. Okay, it's in that state. Here we go. If the maintenance regional headquarters cannot solve the problem, the product is sent to maintenance main headquarters. Okay, if the regional headquarters are unable to repair, it sends it here. This is the state that the item is in at a given time, and we transition between them according to these rules. I think most of you might even find it more helpful to be able to show this up front even than text. But the point is, it shouldn't be rocket science to create a diagram like this at some level. It's not going to be perfect, but it's going to be pretty good. And I give it another example there as well. Okay, from the same book. Okay, now there's some challenges that come up with this. This is not a foolproof method. So one issue is that we sometimes will need states that are history dependent. So there are states that they need to consider something that happened earlier. They're not a determination that's independent of where it's been. It actually needs to take into account where it's been. Or maybe you are just omitting a huge state space in the visual description. Here you're just abstract away from a lot of details. And I would say, like, for the case of the virtual reality thing, there's going to be a large set of actions you can take that they're not going to be fruitful to describe with a graph. It's going to be, what angle are you looking at this underlying system? What level of, zoom or what have you. Those are not going to be that amenable to this discrete description of the states, and that's okay. That's okay. We'll have to find other ways to test some aspects of it. And then sometimes you omit from these things accidentally error transitions or conditions that you perceive as impossible, which are really relevant. So make sure these diagrams do include error states. They include situations where the user has encountered a problem. For example, this invalid contract back here. For example, this case where the user, the card cannot be recognized. You're going to want cases where you're going to have screens if the user has entered, or screens or prompts if the user has entered password incorrectly too many times to log in for the long-term care app, for the admin side, for example, for the admin sort of interface for that, right? You're going to want to be able to indicate that. Or maybe with the Oculus Rift hardware, there's going to be cases where you need to warn the user if the hardware cannot be contacted properly, and therefore it has to default back for the Windows interface or something like that. The hardware is not available. That's a state that this thing could be in. Maybe there's a warning message associated with that. It's a dialog box that pops up and prompts them, pop-up that prompts them to enter something. Please try to make sure that those are in these diagrams. Okay, so let's continue to talk about this though. Okay, so here, and I had a case. Yeah, here it is. Nope, it's one later than this. Okay, I'm surprised it's so much for this is a case where there's a problematic path. Okay, see if you can figure out why there's a problematic path here. So these are transition coverage. This shows paths through the system that exhibit transition coverage. And again, we're focusing on abstract paths. So I'd argue that collectively, the blue, the green, the yellow, and the red, they visit all transitions. Wait, there's one missing. Oh man. Okay, well, modify this for another lecture. There's one that's missing, but otherwise they hit all. But I would argue that there's a problem here with the red one. Why is that a problem? Check out the logic here. So all of them start at the beginning, and they all finish at an appropriate state at that top node. What's the problem with the red one? These are all based on abstractions. So what's the problem here?
Similar to the yellow one again?
Well, okay, it has overlap with the yellow one, but that's actually okay that they have overlap. After all, in that earlier diagram, everything had to flow through, that initial state here. That isn't a problem. It's just a reflection of the fact that to get to places, we have to go through some similar steps. So that actually is a good suggestion, but it's actually not the problem here. What is the problem here?
It looks like it goes from unable to repair to repair and then repaired, which makes it look like their error condition might not be getting handled.
Okay. So actually, good suggestion. Turns out that if we unpack this a bit more, this is being escalated from the maintenance station to the highest level of repair, where they have the best labs to repair it at the main headquarters, and there it is, in fact, getting repaired. So in fact, it is getting repaired, but there's another problem having to do with the logic of it. Take a look at the conditions here. Okay? Could be something to which Canadians are particularly attuned. So the red starts at the top, and then we're going for this wait for pickup state. But that's only available if it's for US or EU residents. Okay? Canadians are not welcome here. Okay? Where this is not an option. It's for US and EU residents. That's okay. Okay. So we hit that state. And then we come down here, it goes to the maintenance station, can't be repaired. And notice, however, that in coming down to the main headquarters, this is also specific to not US or EU resident. Okay. So here, ladies and gentlemen, we have a contradiction. We thought nicely, okay, this path will go through and complete more transitions. But the fact is there's a logical tension here for the conditions under which these two components play out. This one is only allowed for US or EU residents, and this one down here is for cases where it's not a US or EU resident. So there are sometimes cases where you'd like to propose a set of abstract paths, but you got to check the conditions. Can you, in fact, make this path logically, or is that not possible? Any one user, it might be impossible, because they can't simultaneously be a resident and then a non-resident. Okay, so you got to be a little bit careful with that. Sometimes in reasoning about your conditions. Okay, so let's talk about this more here. Okay. So it turns out there's a subsumption relationship here, just like there is that you learned about in 360 or 364 with machines and automata and so on. So, ladies and gentlemen, if we go back to 360, don't worry, I won't tell Mark Kyle your answers. You can close the door there if you want. But remind me with 360 or 364. Thanks. I don't think Mark will come by. He's such a nice guy. I don't think he'd try to go after you if you forgot. So, ladies and gentlemen, give me. So, if we talk about regular expressions and context-free grammars, and we talk about Turing machines, all of those accept languages. They allow us to express languages that we can express. They say that they match certain languages. They succeed for certain languages. Which is more powerful than the other? Is a regular expression, which by the way can be mapped in generative context into a finite state automata, is that less powerful or more powerful than a Turing machine?
Less powerful.
Less powerful. Anything you can do with a finite state automata, you can do with a Turing machine. How about context-free grammar compared to a regular expression? Which can accept a broader set of languages, can express a broader set of languages? Context-free grammar. That's essentially with pushed-on automata, actually, in terms of generating it. And it can express same things we could do with regular expressions. Regular expressions are great for a subset of things. Pushed-on automata and context-free grammars are great for a subset of what Turing machines can do. But they don't handle all cases. And so it is here, ladies and gentlemen. Node coverage is subsumed by everything you could do with node coverage you could do with edge coverage or transition coverage. Okay? So if you achieve transition coverage of your code, assuming that every node is at least one transition into it, if you achieve edge coverage, you have achieved node coverage. If every node is a transition into it, and you've covered every edge, every transition, you've achieved node coverage. A little bit of common sense there. But it turns out there's this whole hierarchy, which is not purely linear here. So, for example, edge pair coverage, achieving all coverage of all possible pairs of edges, that guarantees you edge coverage as well. So if you cover all pairs, cover edge. Prime paths, which we'll be talking about in a later lecture, this gives us another level of power yet. We cover all edge pairs, and all edges, and all nodes. And people in reasoning about what does it mean for a program to be tested have articulated these hierarchies. Now, something that generally is not possible at all is complete path coverage. Why is that? Why can't we completely cover every possible path through a program? Why can't we, achieve full coverage of all possible sort of paths through a program? We could reason about, with an if statement, for example, here to achieve. Give me a path that would achieve edge or state coverage of an if statement here. So this is n1, n0, n1, n2. So give me a path, just listing the nodes appropriate, that will hit all states.
N0 to N1 to N2?
Good. N0, N1, N2. They'll hit all states. How if I want to hit all edges here, or transitions? Give me one or more paths that will hit all transitions.
The one I just gave you plus N0 to N2?
Yeah, N0 to N2. And if we didn't do that, we might miss some really important cases, right? For example, if we were just hitting states and we had code like this, so here we set some pointer to be null, and if a condition is true, then we allocate that pointer, and later we, outside of the if, we dereference that pointer. We assign, into its, we dereference it and set a value into it. Then there's a risk that if we don't test the path where we fall through here, where we don't go in this, that we'll miss a null pointer error. Right? We might miss a null pointer error where we don't, this condition is not true, foo is not true, as shocking as that might be. And we fall through, we never assign p hat to anything but null, and then we assign through it and bad things happen. If we only go, assign this, we simulate the case where it is true, we build the case it is true, we allocate it, and then we go on, things are fine. We've allocated a value and we've assigned to it, so no big deal if you reference it. But it's the case where we fall through that we don't. So this is a case where if you're not testing edge coverage, you are missing some things, right? And you may miss a null pointer exception, which could be fatal. Okay, so ladies and gentlemen, here, hey, where is it? Here. We're talking about exhaustive coverage. Now that's actually exhaustive coverage of these possible transition paths. But let's consider this thing to the right here. So here we have a loop. Suppose that I wanted to have exhaustive coverage of all possible paths through this system. Give me one possible path through this system. Give me one possible path. N2, so this is N0, N1, N2. N2 is the body of the loop. N3 is after the loop. It's sort of left the loop. Give me one path through this. Give me a legal path through this. I'll tell you, N3 is colored with this extra dark thing around it because it's the final path. We enter through N0, we have to leave through N3. So give me one legal path.
0 and 1 and 2 and 1.
That's right. Good. Okay, good. So here, we've gone through the body of the loop once, right? That's covered all states, right? Another possible path that could be taken that doesn't cover all states by itself would be N0, N1, N3, right? But the one that Janelle enumerated, it does cover all transitions. Covered this transition, this one, and that one. Okay, why can't we get all perfect coverage? We cover all possible paths through this thing. Why is that patently impossible here?
Go through the loop.
Yeah, we can't go through the loop any number, in fact, of time. I mean, y could be 10 million or something, and it's, in terms of tests, it's utterly implausible to test it. So we go through the root 0 times, 1 time, 2 times, 3 times, 4 times, all the way up to 10 million. And in general, it's just going to be combinatorially infeasible to test things exhaustively for all possible iterations, numbers of iterations of this thing. So in general, complete path coverage of all logically possible paths is just not going to be feasible. But what we end up doing is we end up taking lower level approximations. And prime paths would be the strongest one that we'll be seeing. Here we're actually systematically identifying paths that are much stronger than just edge coverage or node coverage. They involve a broader sort of basis set of coverage, and even stronger than edge pair coverage. But they still fall far short of complete path coverage. And complete path coverage is utterly infeasible. It's typically just computationally infeasible. There's no way we could test at the level of complete path coverage. We could cover at the level of prime path coverage, okay? We'll be seeing how we do that. Node coverage and edge coverage are the things that I'd ask you to think very seriously about in your projects. At the least, try to get statistics on node coverage. If you can get statistics on edge coverage, what fraction of those transitions, this side of the if statement and that side, that you are actually hitting, that would be superb. But I don't absolutely require it. We will talk about prime path coverage and how to cover it. I don't expect you to be able to achieve that. There are specialized testing tools that can help with that, but I don't expect that as part of this class. Okay? So there is this hierarchy. There's limits to what we can achieve practically in testing. We can't test all possible paths through the program because generally, for some programs, like a read eval print loop and that where you enter things and it gives you the results, or a command line in a shell for an operating system. We just looped forever conceptually. There's no way we can do complete path coverage to cover all possible number of different things we can do. But prime path coverage is pretty darn good, and man, you've ruled out already a lot of types of errors if you have edge coverage. Let me ask this, one final question. We have 1 minute left before the break. Well, we have other classes, yeah. So, ladies and gentlemen, complete path coverage. Let's suppose that we could hit all possible paths through the program. Does that guarantee the program is without bugs? Suppose we did it and we don't get any error messages. All possible paths through the program. Suppose we stand victorious, triumphant. We've done, all complete path coverage because we have a simple enough system that's possible. Does that guarantee the system was without bugs? No. Why not? Suppose it's all successful, all thumbs up. 3 or 4 thumbs up, plus the 2 big toes. Why doesn't that guarantee perfection that we achieve? It indicates our program is devoid of errors.
There could be a path that you're not that you don't one error condition that you don't account for in your code.
Yeah, because other things, ladies and gentlemen, besides paths cause errors. This is abstracting over, is hiding details of what the data is over which you're iterating. Okay, you're hitting each place, but maybe the error is only exposed with certain types of input. And you're not testing those inputs. You're not testing, with empty strings or whatever. So it actually reaches this point and is just happy as a clam. But in fact, if you had tried it with different data, it would have showed an error. So don't get so caught up in thinking edge coverage in any way guarantees that it's correct. It's just that how can we possibly claim that it's correct unless we've at least hit all states? And we've at least made an attempt to hit transitions. I mean, if you've never visited, the admin interface in the latest versions of your long-term care system, you haven't even looked at it. How can you possibly claim our system is robust, right? You have very little basis. But even if you have visited it, that doesn't guarantee it's bug-free. It means you're not embarrassingly impoverished in your testing. At least you've gotten there, once or twice, and at least you've ruled out certain types of errors. So if you can get edge coverage, in my book, you've ruled out significant classes of errors, but you're still vulnerable, and even complete path coverage, even if you could somehow achieve it, for very limited systems, that doesn't guarantee it's bug-free. That, ladies and gentlemen, is a point worthy of an exam. Okay, and with that thought, we now break. Thank you very much. Have a good break.